Picture this: a cosmic snowball drifting through the void of space, trailing a scent so strange it could stop you in your tracks. Rotten eggs, horse stables. Bitter almonds. This isn't some intergalactic garbage dump. It's Comet 67P, one of the most peculiar objects in our solar system. When the Rosetta spacecraft got close enough to sniff it out, scientists were stunned. How could a comet, a frozen relic from the dawn of our solar system, smell like a bizarre cocktail of things you'd find on Earth? But here's the twist: those odors aren't just odd. They're clues. Hidden in that stench are secrets about the very fabric of the universe, mysteries that challenge everything we think we know about physics and chemistry. Comets are supposed to be simple chunks of ice and dust, leftovers from planetary formation. But Comet 67P refuses to play by the rules. Its strange aroma comes from a brew of molecules like hydrogen sulfide, ammonia, and hydrogen cyanide, compounds that shouldn't exist in such quantities on a frozen rock hurtling through space. Even more baffling, the way these chemicals interact defies our current understanding of how matter behaves in extreme conditions. It's as if the comet is whispering a riddle to scientists. You think you've figured out the universe. Think again. So what's really going on here? Why does this comet smell like a chemistry lab gone wrong? And what does it mean for the laws of physics as we know them? Buckle up, because today we're diving into one of space's most head-scratching puzzles. We'll explore the bizarre reactions happening beneath 67P's surface, the theories that leave even experts scratching their heads, and the mind-bending possibility that this comet is hiding something far stranger than we've ever imagined. This isn't just about a smelly space rock. It's about rewriting the rules of reality itself. And by the end of this journey, you'll see the universe in a way you never have before. In 1969, two astronomers peering at grainy photographic plates in the Soviet Union spotted something unexpected, a faint smudge that didn't belong. Klim Churyumov and Svetlana Gerasimenko had just stumbled upon a cosmic wanderer, a comet that would later bear their names. At the time, it was just another frozen speck in the vastness of space, one of countless icy bodies drifting through the solar system. But this one was different. Comet 67P, as it came to be known, had a shape so bizarre it looked like two cosmic rocks glued together, earning it the nickname, the Rubber Duck Comet. And that odd structure was just the first clue that this wasn't your average space snowball. When the European Space Agency began planning its ambitious Rosetta mission, they needed a target that could reveal the secrets of our solar system's infancy. 67P stood out not just for its peculiar shape, but for its orbit, which swung it close enough to the Sun to trigger dramatic changes, yet far enough to preserve ancient chemistry untouched for billions of years. By the time Rosetta launched in 2004, scientists were eager to uncover what this cosmic time capsule could tell us, but no one expected the surprises waiting beneath its dusty surface. The moment Rosetta's instruments got close enough to sniff the comet's gases, the data sent shockwaves through the scientific community. This wasn't just water and carbon dioxide, the usual suspects in a comet's vapor trail. Instead, the spacecraft detected a chaotic mix of chemicals, some so pungent they'd make your eyes water. Hydrogen sulfide, the stench of rotten eggs. Formaldehyde, the sharp bite of a biology lab. Even hydrogen cyanide, the bitter almond aroma that hints at something far more sinister. These weren't just random odors, they were fingerprints of chemical processes no one fully understood, reactions that shouldn't happen in the frozen darkness of deep space. What made these discoveries even more baffling was the comet's dual nature. The rubber duck shape wasn't just for show. It meant two distinct bodies had collided and fused in the early solar system, each with its own unique history. As Rosetta's lander, Phila, touched down, or more accurately, bounced across the surface, it revealed a landscape of cracked cliffs and porous pits where sunlight triggered explosive jets of gas and dust. This wasn't a dead world. It was dynamic, almost alive, with chemistry unfolding in ways that defied textbooks. And that's the real mystery of 67P. Its smell isn't just a curiosity, it's a cosmic breadcrumb trail, leading us toward questions we didn't even know to ask. How could such complex molecules form in the frigid void? What unseen forces are at work in the darkness between stars? Every whiff of that strange, stinky cocktail takes us one step closer to rewriting the story of our solar system, and maybe even the laws that govern it. The Rosetta mission was nothing short of a cosmic detective story, a 10-year chase across 4 billion miles of space to catch a comet in motion. When the spacecraft launched in 2004, its target, Comet 67P, was little more than a blurry speck in telescopes. But engineers had calculated its path with precision, plotting a trajectory that would use Earth's gravity not once, but 3 times as a slingshot to build up enough speed for the rendezvous. By the time Rosetta finally caught up in 2014, the comet was already waking up, its frozen surface cracking as sunlight warmed it for the first time in years. What happened next would rewrite the playbook on how we understand these icy time capsules. Rosetta didn't just observe from a distance, it danced with the comet, matching its orbit with millimeter precision. For nearly 2 years, the spacecraft mapped every crater and cliff, revealing a landscape that looked more like a shattered iceberg than a solid rock. But the real surprises came from its onboard nose, a suite of sensors designed to sniff out gases escaping from the comet's surface. When the data streamed back to Earth, scientists expected to find simple molecules like water vapor and carbon dioxide, the usual suspects in comet tales. Instead, they got a chemical crime scene: hydrogen sulfide, formaldehyde, even whiffs of methanol and acetone, ingredients you'd expect in a poorly ventilated lab, not on a primordial ice ball. The mission's crowning moment came when the tiny lander Phila made its daring descent. Bouncing across the comet's surface like a cosmic pinball, it finally came to rest in a shadowy crevice, where its drills sampled material untouched by sunlight for eons. Those samples contained something astonishing: organic molecules, the building blocks of life, trapped in the comet's icy matrix. Suddenly, 67P wasn't just a curiosity. It was a potential delivery truck for the ingredients that seeded Earth's oceans and atmosphere billions of years ago. But here's where physics starts to scratch its head. These complex molecules shouldn't survive the brutal radiation and vacuum of space, let alone form in the first place. Yet Rosetta's instruments confirmed they weren't contaminants. They were native to the comet, woven into its very fabric. Some scientists now think comets like 67P might be cosmic chem labs, where icy grains act as miniature reactors, shielding delicate molecules long enough for unexpected reactions to occur. Others speculate that the comet's weird rubber duck shape creates hidden pockets where chemistry behaves in ways we've never seen. One thing's certain: Rosetta's discoveries turned comets from simple icy wanderers into active, dynamic worlds. Jets of gas erupt from their surfaces like geysers, sculpting the terrain in real time. Dust particles clump together in defiance of gravity, forming fluffy aggregates that shouldn't exist. And beneath it all, that mysterious stench lingers, a constant reminder that the universe still holds recipes we haven't begun to decipher. Every whiff of rotten eggs or bitter almonds from 67P isn't just a smell. It's a message from the dawn of the solar system, waiting to be decoded. That toxic cocktail wafting from Comet 67P wasn't just unpleasant, it was impossible. On Earth, these smells signal danger. Hydrogen sulfide can suffocate you at high concentrations, ammonia burns your lungs, and hydrogen cyanide is famously lethal. Yet here they were, mingling freely in the vacuum of space, defying every expectation about how chemicals behave in the cosmos. Scientists had assumed comets were essentially dirty snowballs, simple mixtures of water ice and cosmic dust. But 67P's foul bouquet revealed something far more complex brewing beneath its surface. Take hydrogen cyanide, for instance. This molecule requires specific conditions to form, and typically intense heat or electrical discharges like lightning. Yet 67P spent most of its life in the deep freeze of the outer solar system, where temperatures hover near -200 degrees Celsius. How could such a fragile molecule survive billions of years in that environment? One theory suggests these compounds might have formed in the searing heat of the young sun's birth cloud, then somehow got trapped in icy grains that later clumped together to build the comet. But that raises another puzzle. Why didn't they break down over time? Then there's the ammonia mystery. Normally, ammonia molecules should latch onto water ice like magnets, staying frozen solid. Yet Rosetta detected them gushing out as gas, implying some hidden energy source was churning beneath the surface. Some researchers think tiny pockets of radioactive material, left over from the solar system's violent infancy, might still be heating the comet's interior like miniature nuclear reactors. Others propose that when sunlight penetrates the comet's porous crust, it triggers exotic chemical reactions we've never observed in labs, a kind of interstellar alchemy turning simple ices into complex poisons. The strangest clue, the way these smells changed as the comet neared the sun. Like a cosmic mood ring, 67P's emissions shifted dramatically. Hydrogen sulfide spiked while formaldehyde dwindled, as if some unseen switch had been flipped. This wasn't passive evaporation, it was chemistry in action, with molecules breaking apart and recombining in real time. Telescopes even caught brief surges of ethylene glycol, the main ingredient in antifreeze, spraying from cracks in the comet's neck. These unpredictable transformations hint at a dynamic underworld where ices sublimate, gases collide, and reactions unfold in ways our textbooks never predicted. What makes this chemical carnival so groundbreaking isn't just the presence of these molecules, it's their abundance. Space is supposed to be too sparse for complex chemistry, with atoms rarely bumping into each other. Yet 67P's coma proved thicker with organic molecules than the densest industrial smog. Somehow, in the emptiness between stars, nature found a way to brew a noxious perfume more potent than anything we've cooked up in labs. That's why scientists now whisper about dark chemistry, unknown processes that might operate only in the extreme cold and vacuum of space, forging compounds by rules we're only beginning to glimpse. Every whiff from this cosmic dumpster fire forces us to reconsider where complexity comes from. If poisonous molecules can form so readily in comets, could they have seeded Earth's early oceans with the building blocks of life? Or do they point to even wilder possibilities, chemical pathways that don't exist on our planet, hidden in the frozen dark between the stars? 67P's stench isn't just a scientific curiosity, it's a challenge, daring us to rethink how chemistry works when the universe itself is the laboratory. Organic molecules, those fragile, carbon-based structures that form the backbone of life, shouldn't stand a chance in the brutal environment of space. Radiation shreds chemical bonds. Extreme cold slows reactions to a crawl. Yet inside Comet 67P, they not only survived but thrived. When scientists combed through Rosetta's data, they found glycine, the simplest amino acid, floating in the comet's haze. Nearby, phosphorus, a key ingredient for DNA, clung to dust grains. Even more startling were the complex hydrocarbons, chains of carbon atoms that form the skeleton of every living thing on Earth. These weren't random contaminants, they were woven into the comet's icy fabric, preserved like insects in amber for 4.5 billion years. So how did these delicate molecules endure? The secret lies in 67P's icy vaults. Unlike the surface where sunlight triggers violent outbursts of gas, the comet's interior remains frozen solid, a cosmic deep freezer set to -200 degrees. At those temperatures, chemistry moves at a glacial pace, literally. Molecules that would react explosively on Earth become trapped in a kind of suspended animation, shielded by layers of pristine ice. But the real magic happens when sunlight occasionally penetrates. As the comet nears the sun, surface ices sublimate, exposing fresh layers beneath. Buried organic compounds, once locked in stasis, suddenly find themselves in a Goldilocks zone, cold enough to stay intact, but warm enough to mingle. In this fleeting sweet spot, simple molecules link up, forming more complex structures right under our noses. This isn't just theory. Lab experiments here on Earth have recreated the conditions inside comets, blasting icy mixtures with ultraviolet light to simulate cosmic radiation. The results: amino acids form spontaneously, as if the universe has a recipe for life's ingredients written into its very fabric. 67P's chemistry suggests these processes aren't rare, they're inevitable. Every time a comet forms in the icy outskirts of a solar system, it might become a factory for organic molecules, churning out the raw materials for biology before life even exists. That raises a staggering possibility. What if comets didn't just deliver water to early Earth, but the very seeds of life itself? Imagine 67P's ancient cousins bombarding our planet billions of years ago, their icy cargo melting into warm tidal pools. Suddenly, those trapped organic molecules, glycine, phosphorus, hydrocarbons, find themselves in a watery playground, free to combine in ways the frozen void never allowed. It's not proof that comets sparked life, but it's a compelling clue that they could have handed our planet a starter kit. Yet the deepest mystery isn't how these molecules survived, it's how they formed in the first place. Space is vast and empty, with atoms too spread out for complex chemistry. Unless, of course, we're missing something. Some researchers now speculate that comets act like cosmic sponges, soaking up organic molecules from interstellar clouds as they travel. Others think the real action happens on dust grains, where icy coatings provide a staging ground for atoms to meet and bond. Then there's the wild card, quantum tunneling, a phenomenon where particles cheat the rules of classical physics, allowing reactions to occur even in extreme cold. Whatever the mechanism, one thing is clear: 67P's stench is more than a chemical oddity. It's a time capsule from an era when the solar system was a swirling cauldron of potential, and a reminder that the universe seems almost eager to cook up the ingredients for life. Every whiff of rotten eggs or bitter almonds is a whisper from the past, hinting that we might owe our existence to the quirks of cosmic chemistry. Deep in the heart of Comet 67P, buried beneath layers of primordial dust, lies a vault of ancient ice, a time capsule sealed when the solar system was nothing more than a swirling disk of gas and debris. This isn't ordinary ice. Locked within its crystalline structure are molecules that haven't seen sunlight for 4.5 billion years, preserved with near-perfect fidelity. When Rosetta's instruments peered into this frozen archive, they didn't just find water, they uncovered a chaotic menagerie of compounds, some so volatile they should have vanished eons ago. Yet here they were, defying the laws of decay, as if the comet's icy grip could bend the rules of chemistry itself. The magic lies in the extreme cold. At temperatures hovering near absolute zero, chemical reactions slow to a near standstill. Molecules that would normally react in seconds can remain frozen in place for millennia, trapped in a state of suspended animation. But 67P's ice isn't just a passive preserver, it's an active participant in the drama. As the comet swings closer to the sun, sunlight penetrates its porous surface, warming the ice just enough to trigger sublimation. Layers of frozen gas transform directly into vapor, bursting free in geyser-like jets that carry with them traces of the comet's hidden chemistry. Here's where things get weird. Some of the molecules escaping these icy tombs shouldn't exist under these conditions. Take formaldehyde, a simple compound that's notoriously unstable in space. Radiation should tear it apart within days, yet Rosetta detected it pouring out of 67P in surprising quantities. Even more baffling were the complex organics, like methyl isocyanate, a molecule so delicate it's rarely seen outside of laboratories. How could these fragile structures survive the harshness of space for billions of years? One radical theory suggests the ice itself might be playing tricks on physics. In the ultra-cold, ultra-dry environment of a comet's interior, molecules can enter a strange quantum state where they tunnel through energy barriers that would normally block chemical reactions. It's as if the ice provides a secret backdoor, allowing forbidden chemistry to unfold in slow motion. Lab experiments have shown that under similar conditions, simple molecules can link up to form complex chains, no heat or liquid water required. If this quantum chemistry is real, it could rewrite our understanding of how life's building blocks spread through the cosmos. Then there's the ice's structure. Unlike the orderly crystals in your freezer, 67P's ice is amorphous, a chaotic jumble of molecules frozen where they landed, full of microscopic pores and tunnels. These tiny labyrinths might act as protective cages, shielding delicate compounds from radiation while allowing just enough movement for unexpected reactions to occur. Some scientists even speculate that the ice could host exotic phases of matter, like superionic water, a bizarre state where water molecules break apart, allowing oxygen atoms to form a solid lattice while hydrogen ions flow through it like a liquid. The implications are staggering. If comets like 67P can preserve and even foster complex chemistry against all odds, they might be far more than cosmic leftovers. They could be crucibles, forging the raw materials of life in deep space long before planets were ready to receive them. Every puff of gas from this comet's surface is a whisper from the past, hinting at processes we're only beginning to decipher. And hidden in its icy depths might lie answers to questions we haven't even thought to ask. On Earth, chemistry behaves predictably. Heat speeds reactions, cold slows them, and radiation breaks things apart. But step into the shadow of Comet 67P, and those rules crumble. Here, in the frigid embrace of deep space, where temperatures plunge to -200 degrees and cosmic rays bombard every surface, molecules engage in a bizarre dance we barely understand. Scientists call it dark chemistry, a catch-all term for reactions that shouldn't happen, yet do. Picture a factory where workers assemble delicate glass sculptures in a hurricane. That's the improbable reality unfolding on this comet, where fragile organic molecules form and persist against all odds. Take photodissociation, for example. On Earth, ultraviolet light shatters complex molecules like a hammer to glass. But on 67P, something stranger occurs. When sunlight hits the comet's icy crust, it doesn't just break molecules apart, it sparks chain reactions. Free radicals, those hyperactive atomic fragments, skitter across dust grains like molecular pinballs, crashing into other compounds and forging new bonds in the chaos. Lab experiments suggest these frenzied interactions might even build amino acids from scratch, as if the vacuum of space were a cosmic 3D printer for life's ingredients. Then there's surface catalysis, where the comet itself acts as a silent chemist. Unlike Earth's liquid-filled labs, 67P's test tubes are microscopic pores in its dust, tiny crevices where molecules get trapped, forced into close quarters. In these cramped spaces, something extraordinary happens. Normally aloof atoms begin interacting across barriers that should repel them, as if the comet's surface bends the rules of attraction. Some researchers think quantum tunneling might be at play, allowing particles to teleport through energy walls that would block reactions on Earth. The most tantalizing clue lies in the comet's hydrogen cyanide emissions. This deadly compound shouldn't survive long in space, yet it pours from 67P in waves. One theory suggests cosmic rays, typically destroyers of molecules, might paradoxically create them here. As high-energy particles slam into icy grains, they could kickstart reactions that stitch simple atoms into complex chains, like a celestial loom weaving poison from stardust. What makes dark chemistry so revolutionary isn't just its defiance of textbook, it's the implication that the universe operates with a hidden playbook. If comets can brew complex molecules in conditions we'd consider sterile, where else might these rules apply? The icy moons of Jupiter, the clouds between stars. Every whiff of 67P's noxious gases hints that we've barely scratched the surface of cosmic chemistry, and that the universe might be far more inventive than we ever imagined. Hydrogen cyanide is the kind of chemical that sets off alarm bells, a molecule so toxic it was used as a weapon in World War I, capable of shutting down cellular respiration in seconds. Finding it wafting from a comet in deep space is like discovering a loaded gun in a child's toy box. It simply doesn't belong there. Yet Rosetta's instruments detected this lethal compound pouring from 67P in quantities that left scientists stunned. In the cold, sparse environment where comets form, there shouldn't be enough energy or raw material to cook up such a complex poison. Its presence isn't just unexpected, it's a direct challenge to our understanding of how chemistry works beyond Earth. The mystery deepens when you consider how hydrogen cyanide forms. On Earth, it requires either extreme heat, like volcanic vents or industrial furnaces, or electrical discharges like lightning to force nitrogen and carbon atoms into their deadly embrace. But 67P spent most of its life in the frozen outskirts of the solar system, where temperatures hover near absolute zero and sunlight is a faint memory. No volcanoes, no lightning, just an endless, silent chill. So how did this comet become a factory for one of the universe's most efficient killers? One possibility is that the hydrogen cyanide didn't form on the comet at all, it hitchhiked there. In the swirling chaos of the early solar system, the raw ingredients might have assembled in the searing heat near the young sun, where temperatures could reach thousands of degrees. Later, as the solar system cooled, these pre-made molecules could have been flung outward, frozen into icy grains that eventually clumped together to build comets like 67P. It's a compelling idea except for one problem. Hydrogen cyanide is fragile. Over billions of years, cosmic radiation should have torn it apart long before it reached the comet's deep freeze sanctuary. That leaves a far more intriguing alternative. The comet itself might be synthesizing hydrogen cyanide on demand. Recent lab experiments have shown that under conditions mimicking space, simple molecules like formaldehyde and ammonia can undergo bizarre reactions when frozen together and zapped with radiation. The ice acts like a microscopic reactor, channeling energy into specific bonds while shielding others. If similar processes are happening inside 67P, its icy matrix could be quietly assembling deadly poisons from mundane ingredients, a cosmic alchemist turning ice into cyanide. But here's the real twist: hydrogen cyanide isn't just a poison, it's also a building block. This same molecule, so feared for its toxicity, plays a starring role in theories about the origin of life. When mixed with water and exposed to energy, hydrogen cyanide can form adenine, one of the 4 nucleobases in DNA. Suddenly, 67P's deadly secret takes on new meaning. What if this comet isn't just a relic of destruction, but a delivery vehicle for life's ingredients? The same chemistry that churns out poison in the void of space might, under different conditions, lay the groundwork for biology. That duality cuts to the heart of why 67P matters. Its hydrogen cyanide isn't just a scientific curiosity, it's a Rosetta Stone for cosmic chemistry. Whether it formed in the scorching inner solar system or cooked itself up in the frozen dark, its presence forces us to confront how little we truly understand about the universe's hidden chemical potential. Every molecule vented from this comet's surface is a clue and a challenge. If hydrogen cyanide can thrive where it shouldn't, what else are we missing? The answer might rewrite not just the story of comets, but the very origins of life itself. Nitrogen is the quiet architect of life, an essential ingredient in everything from DNA to proteins, yet in space it plays hard to get. Most of the universe's nitrogen floats lazily as a gas, refusing to bond with other elements unless forced. That's why the ammonia pouring from Comet 67P is such a shock. This simple molecule, one nitrogen atom wedged between 3 hydrogens, should be vanishingly rare in the frozen depths where comets form. Yet Rosetta's instruments caught it gushing out like a cosmic geyser, hinting at a nitrogen stash far richer than anyone predicted. The puzzle starts with the birth of our solar system. When the sun ignited, its fierce heat and radiation should have chased nitrogen gas outward, leaving the inner planets nitrogen-starved. Yet here we are, on a world teeming with life built from this very element. For decades, scientists assumed asteroids delivered Earth's nitrogen, but 67P's ammonia outbursts suggest comets might have been secret nitrogen smugglers. The trouble is, current models can't explain how so much nitrogen got trapped in cometary ice. Ammonia freezes at -78 degrees Celsius, warmer than the -200-degree environment where 67P formed. It's like finding an ice cube in a blast freezer, defying the laws of thermodynamics. One radical theory proposes that nitrogen didn't freeze alone, it had help. In the chaotic nursery of the early solar system, tiny dust grains might have acted like molecular Velcro, their jagged surfaces providing just enough grip for nitrogen atoms to cling and react. Laboratory experiments show that under deep space conditions, nitrogen gas can stick to these grains, where cosmic radiation zaps it into ammonia like a celestial chemistry set. Even wilder is the idea that some ammonia formed not in our solar system, but in the frigid womb of the interstellar cloud that birthed it, preserved in icy pockets for billions of years until comets like 67P scooped them up. Then there's the comet's bizarre behavior. As 67P neared the sun, its ammonia emissions didn't follow the expected script. Instead of a steady release, the comet belched sudden plumes, as if nitrogen-rich ices were buried in discrete vaults beneath the surface. Some scientists speculate these might be hotspots, regions where radioactive minerals left over from the solar system's infancy still generate faint warmth, creating localized melt zones in the otherwise frozen interior. Others think the comet's odd, rubber duck shape plays a role, with gravitational stresses squeezing nitrogen reservoirs like a cosmic sponge. The implications ripple far beyond one smelly space rock. If comets hoard nitrogen more efficiently than we thought, they could rewrite the story of how life's building blocks reached Earth. Imagine 67P's ancient siblings bombarding our young planet, their ammonia-laden ice vaporizing in the atmosphere to form nitrogen-rich rain, a primordial fertilizer for the first stirrings of biology. Or consider the possibility that other star systems with different temperatures and chemistries might lock away nitrogen in even stranger ways, reshaping the odds for life across the cosmos. Every whiff of ammonia from 67P forces us to confront the gaps in our cosmic ledger. We've mapped the orbits of planets, probed the hearts of stars, yet something as fundamental as nitrogen's journey remains half-told. This comet's stubborn chemistry hints at hidden chapters, processes we've yet to imagine, operating in the dark corners of space where the rules aren't just different, but waiting to be discovered. Formaldehyde shouldn't be this stubborn. On Earth, it's a fleeting chemical used in labs and factories, sure, but quick to break down or react into something else. Yet aboard Comet 67P, this simple molecule clung on like a cosmic squatter, defying the harshness of space for billions of years. When Rosetta's sensors picked up its unmistakable signature, scientists had to double-check the data. Formaldehyde here in these amounts, it was like finding a lit candle in a blizzard, an anomaly that shouldn't exist, yet undeniably did. What makes formaldehyde so baffling isn't just its presence, it's its resilience. This molecule is the Houdini of organic compounds, notorious for escaping detection. Exposed to ultraviolet radiation or cosmic rays, it typically shatters into carbon monoxide and hydrogen gas. But 67P's formaldehyde wasn't just surviving, it was thriving, emerging in plumes as the comet neared the sun. One theory suggests the comet's icy matrix acts like a cosmic safe deposit box, locking formaldehyde away in microscopic vaults until sunlight cracks them open. Another possibility, the formaldehyde isn't ancient at all. It's being manufactured in real time, forged by reactions we've never witnessed. The plot thickens when you consider where this molecule might have come from. Some researchers argue it's a relic from the primordial solar system, frozen into the comet during its birth. If true, that means formaldehyde was present in the raw materials that built planets, a tantalizing hint that the ingredients for life were baked into the solar system from the start. Others propose an interstellar origin, with 67P scooping up pre-made formaldehyde as it passed through dense molecular clouds. There's even a third, more radical idea, that formaldehyde forms spontaneously on dust grains, where quantum effects allow atoms to tunnel through energy barriers that would block reactions on Earth. But here's the real kicker. Formaldehyde isn't just a passive bystander in the story of life. Under the right conditions, it polymerizes into sugars like ribose, a key component of RNA. That means every whiff of this molecule venting from 67P could represent a missed opportunity, a frozen recipe for biology interrupted by the cold void of space. It's as if the comet is teasing us with what might have been, showing us the unfulfilled potential of cosmic chemistry. The deeper mystery is why formaldehyde persists while other molecules vanish. Is there something special about its structure that lets it cheat decay? Or does the comet's bizarre environment, its porous ice, hidden heat sources, or even its duck-like shape, create niches where fragile molecules get a second chance? Every detection raises new questions, each more perplexing than the last. Formaldehyde shouldn't be here, but it is. And that contradiction might hold the key to understanding how the universe tinkers with life's building blocks when no one's watching. Cosmic rays are the invisible wrecking balls of the solar system, subatomic particles racing at nearly light speed, capable of smashing through solid rock like it's tissue paper. When these high-energy bullets slam into Comet 67P, they don't just leave microscopic pockmarks, they rewrite the comet's chemistry in real time. Imagine a demolition crew that doesn't just tear buildings down, but rearranges the rubble into new, unexpected structures. That's the bizarre alchemy unfolding on this comet's surface, where cosmic rays might be the secret chefs behind its noxious cocktail of gases. For decades, scientists assumed comets were chemically static frozen time capsules preserving ancient ingredients, but Rosetta's data revealed something far more dynamic. The comet's weird mix of molecules, from hydrogen cyanide to formaldehyde, doesn't match what should exist in a simple ball of ice and dust. Now, cosmic rays are emerging as prime suspects in this chemical whodunit. When these particles, mostly protons blasted from distant supernova, collide with molecules on the comet's surface, they don't just break bonds, they spark chain reactions. A single cosmic ray can shatter a water molecule, sending oxygen and hydrogen skittering across the ice. Those rogue atoms then crash into other compounds, forging new molecules that nature never intended to coexist. The smoking gun, laboratory experiments that mimic these conditions. When scientists zap icy mixtures with radiation similar to cosmic rays, they watch in real time as mundane chemicals transform into complex organics. Methanol becomes ethylene glycol, the same antifreeze found spurting from 67P. Ammonia morphs into cyanide. Even amino acids, the building blocks of proteins, materialize from simple ingredients. It's as if the vacuum of space is hiding a clandestine chemistry lab with cosmic rays playing mad scientist. But here's the twist: these reactions shouldn't be so efficient. Space is vast and empty, with molecules spread too thin for frequent collisions. Unless, of course, the comet's surface is acting as a catalyst. 67P's porous, fractal-like terrain creates countless nooks where molecules get trapped, forced into close quarters. Add cosmic rays to this microscopic obstacle course, and suddenly, improbable reactions become inevitable. Some researchers speculate that the comet's dust grains might even act like atomic-scale reactors, their jagged surfaces concentrating energy in ways that bend the rules of chemistry. The implications ripple far beyond one smelly space rock. If cosmic rays can churn out complex molecules on comets, they might be doing the same on asteroids, moons, even interstellar dust clouds. Suddenly, the universe looks less like a sterile void and more like a sprawling chemical refinery, where high-energy particles forge the raw materials for life in the unlikeliest places. Every time 67P exhales a plume of hydrogen cyanide or formaldehyde, it's not just venting gas, it's broadcasting evidence of a hidden cosmic workshop, where the laws of chemistry get rewritten by particles from the depths of the galaxy. That peculiar rubber duck shape isn't just a quirk of Comet 67P, it might be the master key unlocking its bizarre chemistry. Unlike most comets, which resemble lumpy potatoes, 67P's two distinct lobes connected by a skinny neck create a gravitational roller coaster across its surface. Picture pouring water onto a warped table. Instead of spreading evenly, it pools in unexpected places. That's exactly what happens with the comet's volatile gases. Sunlight heats the larger lobe more intensely, while the neck region acts like a cosmic wind tunnel, funneling escaping gases into chaotic jets. The result: chemical hotspots where reactions unfold at dizzying speeds, right alongside frozen wastelands where molecules remain trapped in time. Rosetta's cameras caught this drama in action. As the comet neared the sun, geysers of gas erupted not from its sunny side but from shadowy cracks along the neck, a phenomenon scientists dubbed sun grazing in reverse. These jets carried a cocktail of molecules that shouldn't coexist: water vapor mingling with hydrogen cyanide, carbon dioxide sparring with formaldehyde. The duck shape, it turns out, creates microclimates so extreme they defy textbook chemistry. In one region, temperatures might plunge to -200 degrees, preserving ancient ice. Just a few meters away, sunlight bouncing between the lobes could create tiny ovens, baking trapped molecules into new configurations. The most startling discovery came when scientists mapped the comet's chemical inventory. The smaller lobe was spewing methanol like a cosmic distillery, while the larger one vented sulfur compounds more typical of volcanic vents. This wasn't just uneven distribution, it was as if two different comets had been welded together, each clinging to its own chemical identity. Some researchers now suspect the lobes formed separately in different parts of the solar system, colliding so gently they stuck without fully mixing. If true, 67P isn't just one time capsule, it's two, each with secrets preserved in its own way. Then there's the next role as a chemical crucible. Squeezed by the competing gravities of the lobes, this region undergoes constant stress fractures, exposing fresh ice to space. Every crack becomes a temporary lab where radiation, temperature swings, and trapped gases interact in ways we've never observed on Earth. Experiments suggest these conditions might even trigger cold welding, where dust grains fuse without heat, a process that could shield delicate molecules while allowing bizarre reactions to unfold beneath the surface. What makes this shape so revolutionary isn't just the weird chemistry. It's the realization that comets might be far more than passive ice balls. 67P's duck-like form turns it into a dynamic chemical factory, where geometry dictates which molecules survive and which transform. If that's true, then every oddly shaped comet we've dismissed as a curiosity might be hiding its own unique recipe for cosmic alchemy. The universe, it seems, doesn't need fancy equipment to brew complex chemistry, just a few twists of gravity and light. Comet 67P isn't just a frozen relic, it's a shape-shifting chemical chameleon. As it loops around the Sun on its 6.5-year orbit, this cosmic rubber duck undergoes a dramatic metamorphosis. When Rosetta first arrived in 2014, the comet was still dormant, its surface a silent, frozen wasteland. But as sunlight crept across its jagged terrain, something extraordinary happened. Cracks spiderwebbed through the ice, and geysers of gas erupted like celestial fireworks, spraying plumes of dust half a mile into space. These weren't random outbursts, they followed a precise seasonal rhythm tied to the comet's tortured dance with solar heat. The closer 67P gets to the Sun, the more its personality shifts. In the deep freeze of its outer orbit, only the most volatile gases like carbon monoxide manage to escape, but as temperatures rise, the comet's chemical wardrobe expands. Hydrogen sulfide, the stench of rotten eggs, begins venting from shadowy cracks. Formaldehyde, that sharp preservative smell, surges as sunlight breaks apart more complex molecules. Even methanol, the same alcohol found in antifreeze, starts flowing like a cosmic distillery. These aren't just passive leaks, they're clues to a hidden underground network where ices sublimate, gases collide, and reactions unfold in pockets we can't yet see. What's truly baffling is how localized these changes are. The comet's duck-like shape creates microclimates stranger than anything on Earth. While one lobe bakes in sunlight, the other remains in deep freeze. The narrow neck region acts as a wind tunnel, funneling gases into violent jets that sculpt the landscape below. Rosetta's cameras caught entire cliffs collapsing as trapped gases burst free, revealing pristine ice that had lain untouched for millennia. Each fresh exposure resets the chemical clock, unleashing new reactions as ancient molecules meet sunlight for the first time in ages. The most surprising twist came when scientists compared the comet's summer and winter chemistry. As the smaller lobe reached peak warmth, its vents spewed alcohol and ammonia molecules that typically require liquid water to form. Yet 67P has no liquid water. This suggests some wildcard process, perhaps cosmic rays or quantum tunneling, is enabling chemistry that defies earthly logic. Meanwhile, the larger lobe clung stubbornly to its frozen reserves, only releasing its chemical treasures months later, as if guarding secrets until the last possible moment. These seasonal swings reveal a crucial truth. Comets aren't just icy time capsules. They're active, evolving worlds where chemistry plays out in fast forward as sunlight scripts the reactions. Every orbit, 67P rewrites its own recipe, shuffling molecules like a celestial bartender mixing cocktails with ingredients we've barely begun to catalog. And hidden in those shifting chemical signatures might lie answers to how life's building blocks survive and thrive in the unlikeliest corners of the cosmos. Of all the strange odors wafting from Comet 67P, none stings the nose or puzzles scientists quite like hydrogen sulfide. That unmistakable rotten egg stench shouldn't be so strong on a comet billions of miles from Earth's swamps and volcanoes. Yet Rosetta's sensors detected it in startling abundance, alongside other sulfur compounds like sulfur dioxide and carbon disulfide. This isn't just a whiff of cosmic flatulence, it's a full-blown chemical anomaly. Most comets contain mere traces of sulfur, if any at all, but 67P reeks of it, as if someone dumped a truckload of matches into its icy core. So where's all this sulfur coming from? The leading theory takes us back to the comet's birth, 4.5 billion years ago. In the swirling disk of gas and dust that formed our solar system, temperatures weren't uniform. Near the young sun's furnace-like heat, sulfur existed mostly as a gas, but farther out, in the frozen realm where comets took shape, it could freeze onto dust grains alongside water and methane. If 67P formed near a pocket of these sulfur-rich ices, it might have gobbled them up like a cosmic sponge, preserving the element in its frozen vaults. There's a twist, though. Sulfur is notoriously fickle in space. Exposed to ultraviolet light or cosmic rays, it readily bonds with hydrogen to form hydrogen sulfide, or with carbon to create carbon disulfide. That means the sulfur we smell today might not be the sulfur the comet started with. Over eons, radiation could have transformed primordial sulfur compounds into the cocktail we detect now, like a slow-motion alchemy experiment playing out in deep freeze. The most tantalizing clue lies in the sulfur's uneven distribution. Rosetta found hydrogen sulfide concentrated in the comet's neck region, while sulfur dioxide favored the larger lobe. This patchwork pattern suggests the sulfur didn't arrive in one uniform package. It might tell a story of two distinct origins. Perhaps the lobes formed in different parts of the protoplanetary disk, each sampling unique sulfur reservoirs before colliding to create the duck-shaped oddity we see today. What makes this sulfur saga so pivotal isn't just the comet's stench, it's the implications for life's origins. Sulfur plays a starring role in biology, from the iron-sulfur clusters that power our cells to the amino acids that build proteins. If comets like 67P delivered sulfur to early Earth, they might have supplied more than just water. They could have provided the spark for life's chemical machinery. Every whiff of rotten egg from this cosmic rubber duck isn't just a mystery, it's a potential clue to how the universe seasons the recipe for life itself. Water ice should be straightforward frozen H2O, the same substance that fills Earth's oceans and glaciers. But Comet 67P's water isn't playing by the rules. When scientists analyzed its isotopic fingerprint, they got a shock. the ratio of heavy water molecules containing deuterium, a heavier form of hydrogen, was 3 times higher than in Earth's oceans. This tiny difference might seem insignificant, but it's a cosmic deal-breaker. If comets like 67P were the primary delivery trucks for Earth's water, their isotopic signatures should match. The mismatch suggests that either this comet is an oddball, or we've been wrong about where our planet's water truly came from. The plot thickens when you consider how water behaves on 67P's surface. Unlike the orderly ice cubes in your freezer, this comet's water exists in a state of constant flux. During the day, sunlight transforms surface ice directly into vapor, creating geysers that blast dust into space. At night, the water vapor refreezes, but not where you'd expect. Instead of forming a smooth layer, it clings to dust grains in bizarre, porous structures resembling cosmic cotton candy. These fluffy ice-dust hybrids have bizarre properties. Lab experiments show they can trap other molecules inside their labyrinthine structures, creating microscopic reaction chambers where chemistry unfolds in ways impossible on Earth. Even stranger is how water interacts with the comet's other ingredients. On Earth, water is the universal solvent, effortlessly dissolving salts and sugars. But on 67P, it's more like a chemical conspirator. When water ice and carbon dioxide freeze together in the comet's shadowy cracks, they form a peculiar hybrid ice called a clathrate, a cage-like structure where CO2 molecules get trapped inside water's crystalline lattice. These clathrates aren't just curiosities, they're cosmic pressure cookers. As the comet warms, the trapped gases explode outward, fracturing the ice and exposing fresh surfaces for more reactions. It's a self-perpetuating cycle that turns the comet's water into both a chemical ingredient and a demolition crew. The most tantalizing possibility lies in what these processes mean for life's origins. If 67P's water can shelter and rearrange molecules so effectively, could other comets have done the same for Earth? Even if this particular comet didn't deliver our oceans, its chemistry hints at a hidden talent comets might share, acting as cosmic incubators where water doesn't just exist, but actively engineers complexity. Every time 67P's icy surface erupts in a sunlit jet, it's not just venting water vapor, it's demonstrating how the universe's most mundane molecule might also be its most ingenious chemist. Beneath the chaotic jets and plumes of Comet 67P lies an unsung hero, its dust. Far from being inert debris, these microscopic grains are bustling chemical factories, each one a stage where the universe's strangest reactions play out. Picture a grain no wider than a human hair, pitted and porous like a cosmic sponge. Its surface is a labyrinth of cracks and crevices where molecules huddle together, shielded from the vacuum of space. Here, in these miniature caves, the rules of chemistry bend. Atoms that would never interact in the void suddenly find themselves pressed shoulder to shoulder, forced into alliances that defy expectation. What makes these dust grains so revolutionary is their role as catalysts. On Earth, we rely on rare metals like platinum to accelerate reactions, but 67P's dust achieves the same feat through sheer geometry. Those jagged edges and honeycomb tunnels act like molecular meeting rooms, trapping ingredients long enough for magic to happen. Laboratory experiments show that when simple ices like water and methanol freeze onto similar grains, cosmic radiation can transform them into complex organics: acetic acid, glycine, even the building blocks of RNA. It's as if every speck of dust is a tiny alchemist, turning cosmic leftovers into compounds that shouldn't exist in deep space. The comet's strangest emissions might owe their existence to this gritty chemistry. Take formaldehyde, a molecule Rosetta detected in surprising quantities. On Earth, it forms in controlled industrial processes, but on 67P, it could be assembling spontaneously on dust grains. As ultraviolet light or cosmic rays zap these tiny platforms, they knock atoms loose, allowing them to recombine into new configurations. Some researchers speculate that the grain's uneven surfaces might even concentrate energy like microscopic lenses, creating hotspots where reactions ignite against all odds. Then there's the mystery of molecular oxygen. When Rosetta found O2 gushing from the comet, scientists were floored. Oxygen is notoriously reactive, quick to bond with other elements. Yet here it was, pouring forth as if the comet had secret reserves. The answer might lie in the dust. As water ice sublimates from these grains, it could leave behind tiny pockets of pure oxygen, trapped like bubbles in cosmic amber. Over millennia, these reservoirs build up, only to burst free when sunlight cracks them open. But the real marvel is how these processes scale up. Individually, each grain is insignificant, but collectively, they form a chemical network spanning the entire comet. A single cubic meter of 67P's surface contains trillions of these particles, all humming with activity. Together, they create a feedback loop. As gases erupt, they carry dust aloft, exposing fresh surfaces to sunlight and radiation, which in turn spark new reactions. It's a self-sustaining cycle that turns the entire comet into a sprawling chemical reactor. This gritty alchemy might solve one of astrobiology's biggest riddles: how life's ingredients spread through the cosmos. If dust grains can forge complex molecules in the harshness of space, then comets like 67P aren't just bystanders in the story of life. They're delivery vehicles, scattering prebiotic material across star systems with every orbit. Every time this cosmic rubber duck sheds a layer of dust, it might be seeding the universe with the seeds of something far greater. The surface of Comet 67P is a study in cosmic contradictions. One moment plunged in permanent shadow where temperatures hover just 30 degrees above absolute zero. The next moment blasted by unfiltered sunlight that can heat exposed patches to a relatively balmy 50 degrees Celsius. That's a swing more extreme than any desert on Earth, and it's not just a weather report, it's a recipe for chemical chaos. When materials experience such violent temperature shifts, they don't just expand and contract, they behave in ways that rewrite the rules of physics as we know them. Take water, for instance. On Earth, it follows predictable phase changes, solid to liquid to gas. But in the vacuum of space, with no atmospheric pressure to mediate the process, 67P's water ice doesn't melt. It sublimates directly from solid to vapor in explosive bursts. This sudden transformation creates a domino effect, exposing deeper layers of ice to sunlight, which then undergo their own violent phase changes. The result isn't a gentle thaw, but a chain reaction of miniature explosions across the comet's surface, each one blasting trapped molecules into space like a cosmic pressure cooker venting steam. These temperature swings do more than just release gases, they create bizarre new materials. Laboratory experiments simulating comet conditions reveal something startling. When mixtures of water, ammonia, and methanol are repeatedly frozen and warmed in a vacuum, they form strange hybrid ices with properties unlike anything found on Earth. Some develop honeycomb structures that trap other molecules like flypaper. Others become electrically conductive, allowing chemical reactions to propagate through the ice like currents through a wire. If similar processes are happening on 67P, its wild temperature swings might be assembling complex molecules right under our noses. The most tantalizing possibility lies in what scientists call non-equilibrium chemistry, reactions that only occur when a system is violently pushed out of balance. On Earth, most chemistry happens at equilibrium, where temperatures and pressures are relatively stable. but 67P's seesawing temperatures create brief, intense windows where molecules interact in ways that would otherwise be impossible. Imagine a dance floor where the music keeps switching between a waltz and a mosh pit. Partners that would never normally interact suddenly find themselves forced together, creating unexpected new combinations. This could explain some of the comet's most puzzling chemical signatures. The hydrogen cyanide that pours from its surface, for example, might form when nitrogen and carbon compounds get violently shaken together during temperature spikes, their bonds rearranged by the energy of sudden heating. The formaldehyde detections could come from methanol molecules fractured by rapid cooling, their broken pieces reassembling into new configurations. Even the comet's sulfur compounds might owe their existence to these extreme cycles, with temperature swings acting like a cosmic forge, hammering simple elements into complex poisons. What makes this discovery so groundbreaking isn't just the chemistry, it's the realization that stability might be the exception, not the rule in the universe. For centuries, we've studied reactions under controlled lab conditions, assuming they represented nature's baseline. But 67P screams otherwise. Its entire existence is a testament to how much we've underestimated the creative power of chaos. Every time this cosmic rubber duck swings around the sun, it doesn't just lose ice, it becomes a temporary alchemy lab, where the universe experiments with recipes we're only beginning to decipher. Comet 67P might hold more than just secrets from our solar system's infancy. It could be carrying whispers from another star entirely. The idea that this cosmic rubber duck contains interstellar ingredients isn't science fiction. It's a serious hypothesis gaining traction among astronomers. When the sun and planets formed, they condensed from a swirling molecular cloud, a nursery of gas and dust that likely harbored fragments from even older stellar systems. Some researchers now suspect 67P's peculiar chemistry, especially its bizarre mix of organic molecules, might be fingerprints of that ancient inheritance, preserved like cosmic heirlooms in its icy depths. The clues lie in the comet's molecular oddities. Take its deuterium to hydrogen ratio, a chemical signature that's wildly different from Earth's oceans and most other comets studied so far. This mismatch suggests the water ice in 67P didn't originate in the same neighborhood as the rest of our solar system. Instead, it might have formed in the frigid outskirts of that primordial molecular cloud, where temperatures and radiation levels allowed exotic isotopes to accumulate. Even more telling are the comet's complex organics, like methyl isocyanate and acetone compounds that typically require specific, energy-rich environments to form. These molecules are rare in our solar system but have been detected in interstellar space, hinting at a possible foreign origin. Supporting this theory are lab experiments that recreate the conditions of interstellar clouds. When scientists expose icy mixtures to the extreme cold and radiation of deep space, they produce a cocktail of organics eerily similar to what Rosetta found on 67P. This suggests the comet's chemistry might not be homegrown at all, but rather a relic of processes that occurred before the sun even ignited. Imagine a snowflake drifting through the galaxy for millions of years, collecting the signatures of distant cosmic events before finally being swept up into the solar system's construction site. That could be the story locked inside this comet's ice. The implications are staggering. If 67P truly carries material from beyond our solar system, it becomes a time capsule not just for our own cosmic backyard, but for the entire galactic neighborhood. Its ices could preserve chemistry from a time when our corner of the Milky Way looked utterly different, when other stars, now long dead or distant, contributed their own raw materials to the mix. This wouldn't just rewrite the comet's history. It would mean the building blocks of life on Earth might have interstellar pedigrees, forged in the hearts of alien molecular clouds before hitchhiking here aboard comets like 67P. Yet the mystery deepens when we consider how this material survived. The violence of star formation, the shockwaves, radiation, and gravitational turmoil should have scrambled or destroyed delicate interstellar molecules. That they endured suggests 67P's ices acted as a cosmic freezer, locking in fragile compounds before the chaos of the solar system's birth could erase them. Alternatively, the comet's duck-like shape might have shielded certain regions, creating pockets where pristine material remained untouched while the rest of the solar system churned and mixed. Whether or not 67P proves to be an interstellar immigrant, its chemistry undeniably challenges our assumptions about the boundaries of our cosmic home. Every plume of gas, every whiff of its strange aroma, carries echoes of processes that might have begun light years away. This comet isn't just a messenger from the solar system's past, it could be a diplomat from realms we've only begun to explore. The Philae lander's bumpy touchdown on Comet 67P in November 2014 was anything but textbook, a harrowing series of bounces that left it wedged in a shadowy crevice, solar panels barely catching the sun. Yet in those frantic 60 hours before its batteries died, this washing machine-sized probe delivered a treasure trove of contradictions. Its instruments scraped against a surface harder than expected, not the fluffy snowbank scientists predicted, but an icy crust tough as asphalt, laced with organic molecules that glinted like cosmic graffiti in the lander's spectrometers. Then silence. Phila slipped into hibernation, its most tantalizing data trapped in memory banks that might never wake. But what little escaped before the blackout paints a revolutionary picture. This comet isn't just a frozen relic, it's a layered archive with chemistry varying wildly from patch to patch. One of Philae's most startling discoveries came from its MUPUS instrument, a hammer-like probe designed to measure surface hardness. When it attempted to drive into the comet's skin, it barely made a dent, revealing a crust 20 times stronger than predicted. This wasn't loose powder, it was ice compressed over eons, perhaps cemented by organic glue. Nearby, the Cossack instrument sniffed out 16 organic compounds, including 4 never before detected on a comet. Among them, acetamide, a molecule linked to amino acids, and methyl isocyanate, a toxic compound that's also a building block for peptides. These weren't random contaminants, they clustered in discrete patches like chemical islands in an icy sea. The real bombshell lay in what Phila almost told us. Buried in its final transmissions were hints of porous chambers beneath the landing site, voids where gases might accumulate, creating hidden pressure cookers for chemistry. Had Phila's drill succeeded in delivering a sample to its ovens, we might have known for sure. Instead, we're left with spectral ghosts, tantalizing spikes in the data suggesting complex organics too heavy to vaporize in the instrument's heat. Some scientists now speculate these could be polymers or even probiotic chains, frozen in the act of assembling into something more profound. What makes Phila's unfinished story so haunting isn't just the data we lost, it's the patterns in what little we have. Every measurement hints at a comet more chemically diverse than models predicted. The hard, organic-rich patches near Phila's final resting place contrast sharply with the fluffy dust Rosetta observed elsewhere, suggesting 67P isn't a uniform snowball but a palimpsest of different environments, each preserving distinct chapters of solar system history. Even the lander's misfortune, its awkward angle, became accidental genius. By peering sideways at the comet's strata, it revealed layers with varying reflectivity, like pages in a book we've only glimpsed the margins of. The greatest mystery, whether Phila's silent servers still hold answers. In 2016, as the comet neared the sun, engineers caught a fleeting whisper, a 2-minute connection where the lander briefly stirred. just enough to confirm its systems, still intact, had recorded months of data during a surprise power-up. Then, radio silence forever. Somewhere in that frozen crevice, a trove of temperature readings, gas measurements, and perhaps even partial drill results lies frozen in silicon, waiting for a future mission to retrieve it. Until then, those 60 hours of frantic data remain a cosmic cliffhanger, proof that 67P's wildest secrets might still be buried, not in ice, but in the ones and zeros of a sleeping spacecraft. One moment, Comet 67P is drifting silently through space. The next, it erupts without warning. These aren't the predictable geysers triggered by sunlight. These outbursts are violent, chaotic explosions, blasting plumes of gas and dust thousands of kilometers into space. In July 2015, Rosetta's cameras caught one such event in real time, a sudden jet erupting from the comet's neck region, hurling debris at speeds over 10 meters per second. What made this eruption so baffling wasn't its power, but its timing. The outburst occurred when that part of the comet was in shadow, ice still frozen solid. No solar heat could explain it. Something far stranger was at work beneath the surface. These outbursts follow no predictable schedule. Some last mere minutes, while others rage for hours. The gases they release aren't just water vapor, but a chaotic mix of carbon dioxide, carbon monoxide, and organic compounds, almost as if the comet is coughing up pockets of ancient chemistry preserved in its icy depths. Scientists have mapped dozens of these events, tracing their origins to specific fractures and pits. Yet the triggers remain elusive. One theory points to trapped volatile ices, like carbon dioxide or nitrogen, which can sublimate explosively when exposed to sudden warmth. Another suggests pockets of pressurized gas, sealed beneath layers of ice for millennia, until the comet's shifting structure cracks them open like a shaken soda bottle. The most tantalizing possibility involves the comet's bizarre internal chemistry. Lab experiments show that mixtures of water ice, organic compounds, and minerals can generate heat as they interact, a slow burn of molecular rearrangements. If similar reactions are simmering beneath 67P's surface, they might create hidden reservoirs of energy, waiting for a weak spot in the ice to unleash their fury. Some researchers even speculate about cryovolcanism, a phenomenon where ices, rather than molten rock, erupt like lava, carrying slurries of exotic chemistry to the surface. What makes these outbursts revolutionary isn't just their violence, it's what they imply about comets' hidden lives. If 67P can erupt without solar prompting, then comets might be far more than passive ice balls waiting for sunlight to wake them. They could be ticking time capsules, their interiors seething with pent-up energy and chemistry we've yet to comprehend. Every jet of gas, every plume of dust is a message from the dark, proof that even in the coldest corners of the cosmos, the universe never sleeps. Magnetic fields around Comet 67P shouldn't exist, at least not in any meaningful way. Unlike planets with molten cores or stars with churning plasma, this rubber duck-shaped ice ball lacks the internal machinery to generate strong magnetism. Yet when Rosetta's sensors swept over the comet, they picked up faint but undeniable magnetic whispers threading through its coma, the cloud of gas and dust surrounding its nucleus. These fields are vanishingly weak, about 50,000 times weaker than Earth's protective magnetic shield, but their mere presence hints at an invisible force quietly shaping the comet's chaotic chemistry. What's generating these fields? The answer lies in the comet's dance with the solar wind, a relentless stream of charged particles racing from the sun. As these high-energy electrons and ions slam into 67P's coma, they don't just collide with gas molecules, they electrify them. Neutral atoms get stripped of electrons, transforming into ions that spiral along newly created magnetic field lines like cars on a cosmic freeway. This process, called ionization, turns the coma into a makeshift magnetosphere, a wispy, transient version of the magnetic bubbles surrounding planets. The real magic happens in the details. Rosetta's measurements revealed these fields aren't uniform. They're tangled and patchy, stronger near sudden gas jets and weaker over icy plains. This unevenness suggests the magnetic environment is dynamic, flickering in and out of existence as the comet's activity changes. During outbursts, when 67P spews fresh gas into space, the fields briefly intensify, as if the coma is momentarily turbocharging its own magnetic influence. But here's the puzzle. These faint fields shouldn't have much sway over the comet's chemistry. Yet researchers noticed curious correlations. Regions with stronger magnetism tended to have higher concentrations of certain ions, like water group ions and carbon dioxide ions. It's as if the fields are acting like cosmic bouncers, herding specific molecules into clusters while letting others drift freely. Some scientists speculate this selective gathering could create microscopic hotspots where rare reactions occur, allowing fragile compounds to form that would otherwise vanish in the vacuum. Laboratory experiments back this up. When researchers simulate comet conditions with weak magnetic fields, they observe something peculiar. Ions move differently. Instead of scattering randomly, they follow spiraling paths that increase their chances of colliding and reacting. In the vast emptiness of space, where atoms might go millennia without bumping into each other, even a faint magnetic nudge could dramatically boost the odds of chemical meetups. The implications ripple beyond 67P. If weak magnetism can subtly steer chemistry on comets, it might do the same in interstellar clouds or on icy moons. These findings challenge the assumption that significant magnetic influence requires planetary-scale strength. Sometimes, the universe works its quietest magic with the softest touch. Every time this comet's wispy fields rearrange a molecule's path, they're proof that even in the darkest corners of space, nothing truly moves alone. Most comets follow a predictable script: frozen leftovers from the solar system's birth, trailing tails of vaporized ice as they near the sun. But Comet 67P refuses to conform. Place it side by side with famous visitors like Halley or Hale-Bopp, and the differences leap out. Halley, that celestial celebrity with its 76-year orbit, spews mostly water vapor and carbon dioxide, classic comet fare. Hale-Bopp dazzled with its twin tails of dust and ionized gas, but its chemistry was textbook. Then there's 67P, the cosmic rebel, stinking of rotten eggs and bitter almonds, its rubber duck silhouette defying every expectation. The contrasts run deeper than appearances. Halley's nucleus, though dark and cratered, is relatively uniform, a single chunk of ice and dust. 67P's two-lobed structure suggests a violent past, a slow-motion collision that left it forever lopsided. Even their surfaces tell different stories. Where Halley's jets erupt symmetrically, 67P's geysers burst unpredictably from its neck, as if some hidden pressure cooker beneath the ice is venting its fury. Chemistry seals the case. While most comets carry traces of simple organics, 67P's cocktail includes methyl isocyanate and acetone compounds so complex they're typically found in industrial labs, not drifting ice balls. Hale-Bopp's famous cyanogen and diatomic carbon emissions painted its coma a eerie green, but they paled next to 67P's hydrogen sulfide plumes, which reeked of a cosmic sewer. So why the divergence? One theory points to birthplace. Halley likely formed in the Kuiper belt, that icy fringe beyond Neptune, while 67P may have originated farther out, in the scattered disk, a region where the sun's influence wanes and interstellar chemistry creeps in. Another possibility is age. 67P's peculiar shape hints at a traumatic youth, perhaps a collision that scrambled its original composition. Or maybe it's the comet's porous interior, creating sheltered niches where dark chemistry brews undisturbed. The most tantalizing idea, 67P isn't an outlier, it's a missing link. Most comets we've studied up close are short-period visitors, tempered by repeated solar encounters. 67P, with its longer orbit, might preserve a purer snapshot of primordial chemistry. Its stench, its shape, its chaotic eruptions, they're not anomalies but echoes of a time when all comets were this wild. By comparing these cosmic snowballs, scientists aren't just cataloging differences. They're piecing together a solar system family album, one where 67P's quirks might reveal what the rest have forgotten. Every whiff of its sulfurous breath, every jagged cliff on its duck-shaped surface, whispers secrets about where we all came from. The story of Comet 67P begins not with a single moment of creation, but with a slow, cosmic waltz in the frigid outskirts of our solar system. Most scientists agree this rubber duck-shaped wanderer took shape in one of two icy sanctuaries, the Kuiper Belt, that donut-shaped ring of frozen debris beyond Neptune, or the even more distant scattered disk, where objects drift at the very edge of the sun's gravitational embrace. These regions are nature's deep freezers, preserving ingredients from the solar system's infancy at temperatures barely above absolute zero. Under such conditions, chemistry moves at a glacial pace, allowing delicate molecules to survive untouched for billions of years. That's why comets like 67P are considered time capsules. Their ices and dust could hold pristine samples of the raw materials that eventually built planets like Earth. Yet from the moment Rosetta began analyzing this comet's composition, it became clear something didn't add up. The mix of water isotopes, the abundance of complex organics, even the lopsided distribution of sulfur compounds, they all point to an origin story more complicated than the standard Kuiper Belt narrative. For instance, the comet's deuterium to hydrogen ratio, a kind of chemical fingerprint, is wildly different from other comets studied so far. This mismatch suggests 67P didn't form in the same neighborhood as its peers, but perhaps migrated inward from colder, more distant reaches where isotopic ratios skewed differently. Then there's the comet's bizarre shape, two distinct lobes connected by a fragile neck, resembling a celestial snowman mid-collapse. Most models of comet formation assume these bodies start as roughly spherical agglomerations of ice and dust. 67P's two-part structure hints at a dramatic past, possibly a slow-motion collision between two separate cometesimals that gently stuck together rather than shattering. This would make it a cosmic Frankenstein, stitched together from mismatched parts in the solar system's chaotic youth. The real enigma lies in the comet's chemistry. While most Kuiper Belt objects contain simple ices like water, carbon dioxide, and methane, 67P is laced with compounds that typically require energy to form hydrogen cyanide, formaldehyde, even acetone. These molecules shouldn't thrive in the frozen dark where comets are born. One provocative theory suggests the comet might have formed near the boundary of the protoplanetary disk, where temperatures and radiation levels created a Goldilocks zone for complex chemistry. Alternatively, it could have spent time closer to the young sun before being hurled outward by gravitational interactions with giant planets, picking up exotic molecules along the way. Perhaps the most radical idea is that 67P isn't purely a product of our solar system at all. Some of its organic compounds, like methyl isocyanate, have been detected in interstellar molecular clouds. Could this comet have inherited material from the vast cloud that birthed our sun, preserving chemistry that predates the planets themselves? Lab experiments show that ultraviolet radiation and cosmic rays can transform simple interstellar ices into complex organics, exactly the kind of molecules Rosetta found. If true, 67P might be less a solar system relic and more an interstellar immigrant, carrying secrets from beyond our cosmic neighborhood. What's certain is that this comet refuses to fit neatly into any existing category. Its peculiarities force us to reconsider not just where comets form, but how diverse their origins might be. The early solar system wasn't an orderly factory assembly line. It was a chaotic marketplace of drifting ices, migrating planets, and violent collisions. 67P's strangeness might not be an anomaly, but a reminder of how much we've underestimated that chaos. Every time this cosmic rubber duck swings past the sun, venting its odd mix of gases, it's not just releasing vapor, it's exhaling clues about a past far more complicated than we ever imagined. Rosetta's dramatic finale, a controlled crash into Comet 67P's dusty surface in 2016, was never meant to be the end of the story. That mission rewrote the textbooks on comets, but it also left burning questions hanging in the cosmic air. What lies beneath that bizarre rubber duck surface? How do complex molecules survive in the void? And most tantalizing of all, could comets like 67P hold the master key to understanding how life's ingredients spread through the solar system? Scientists aren't just dreaming about answers, they're building the next generation of spacecraft to hunt them down. The European Space Agency is already sketching plans for a Rosetta successor called Comet Interceptor, designed to ambush a pristine comet entering the inner solar system for the first time. Unlike 67P, which has been weathered by countless solar passes, these virgin comets might preserve chemicals unchanged since the dawn of our solar system. But the real holy grail, a sample return mission. Imagine a drill penetrating 67P's neck region, where Phila detected those strange organics, scooping up icy chunks and rocketing them back to Earth for analysis. Lab instruments here could detect trace compounds Rosetta's sensors missed, potentially uncovering amino acids or other prebiotic molecules in their native state. Meanwhile, NAS, a concept for a cryogenic comet nuclear sample return, takes this idea even further. This ambitious mission would capture not just surface material, but deep core samples kept at cryogenic temperatures to prevent volatile compounds from escaping. Picture a spacecraft equipped with a thermal drill that gently bores into the comet's heart, extracting pristine ice that's been sealed away for billions of years. The technical challenges are staggering, keeping samples cold during the years-long journey home, preventing contamination, but the payoff could revolutionize our understanding of cosmic chemistry. Some proposals go even bolder. The Breakthrough Starshot Initiative, best known for its interstellar ambitions, has studied using laser-propelled microprobes to swarm a comet like 67P. Thousands of smartphone-sized sensors could blanket its surface, mapping chemical hotspots in unprecedented detail. Another radical idea involves comet hitchhikers, landers that use harpoons and tethers to hop between different regions, comparing the chemistry of the duck's head versus its body in real time. The driving force behind these missions isn't just curiosity, it's 67P's stubborn refusal to fit our models. Every anomaly it revealed, from its magnetic whispers to its sulfurous outbursts, hints at processes we've barely begun to understand. Future spacecraft might carry miniaturized labs capable of replicating comet conditions on the spot, testing whether amino acids really can form in those icy pores. Others could deploy seismic sensors to listen for the groans and cracks of shifting subsurface chambers, revealing the hidden architecture that shelters these delicate molecules. What makes this next era so thrilling isn't just better technology, it's the chance to see comets as dynamic worlds, not frozen relics. Imagine watching 67P's chemistry change across an entire orbit, or drilling into one of its mysterious cryovolcanoes as it erupts. The data waiting to be uncovered could rewrite not just comet science, but our very understanding of how chemistry behaves when the universe itself is the laboratory. Every strange molecule, every unexplained plume, is a signpost pointing toward discoveries we can't yet imagine, and the next missions will follow them deep into the unknown. The discovery of complex organic molecules on Comet 67P doesn't just rewrite the rules of chemistry, it reshapes our understanding of life's cosmic potential. If this smelly, duck-shaped ice ball carries amino acids, phosphorus, and hydrocarbons, then comets like it could have been interstellar couriers, delivering life's raw materials to Earth billions of years ago. But here's the staggering implication. If one comet holds these ingredients, countless others might too, scattered across star systems like cosmic grocery stores stocking the universe's pantry. The building blocks of biology may not be rare treasures, they could be as common as stardust. Consider the numbers. Our solar system's Oort cloud alone may harbor trillions of comets, each a potential time capsule of prebiotic chemistry. Multiply that across the Milky Way's hundreds of billions of stars, and the statistical likelihood becomes undeniable wherever planets form. Comets are probably there too, seeding them with life's starter kit. 67P's sulfurous belches and cyanide-laced plumes suddenly look less like oddities and more like universal recipes, written into the fabric of star formation itself. Yet mysteries remain. Having the ingredients is one thing, knowing how they become life is another. Laboratory experiments show that comet-like ices bombarded with radiation can produce amino acids, but can these molecules survive the journey to a planet's surface? Phila's data hints at a possible answer. The comet's porous, layered structure might protect fragile organics during atmospheric entry, shielding them like microscopic escape pods. And once delivered, comets could have provided more than just molecules. Their impacts may have created hydrothermal vents, the very environments where life's first spark could catch. The search for extraterrestrial life now has a new roadmap. Instead of just hunting for liquid water or oxygen, astrobiologists are scanning distant cometary belts for chemical fingerprints matching 67P's. The James Webb Space Telescope recently detected complex organics in a protoplanetary disk 500 light-years away, suggesting this chemistry begins even before planets finish forming. Future missions to icy moons like Europa or Enceladus will carry instruments fine-tuned to detect comet-delivered molecules, tracing the breadcrumbs life might have followed across the cosmos. But the most profound revelation lies in the timeline. 67P's chemistry suggests the universe didn't wait for Earth to experiment with life. It had been tinkering for billions of years, testing combinations in the frozen dark. Every time this comet vents formaldehyde or hydrogen cyanide, it's not just exhaling gas, it's whispering that the difference between sterile chemistry and biology might be thinner than we ever dared hope. Physics textbooks paint a tidy picture of how matter should behave: predictable phase changes, orderly reactions, and energy states that follow well-defined rules. But Comet 67P didn't read those textbooks. This cosmic maverick operates on a different playbook, one where chemistry defies expectations and physics bends in ways that leave researchers scrambling for new theories. Take its molecular cocktail, for instance. On Earth, hydrogen sulfide and ammonia rarely coexist in the same environment without reacting violently. Yet inside 67P, they mingle freely, trapped in an icy matrix that somehow preserves their incompatible natures. It's like finding oil and water refusing to separate, a violation of conventional chemistry that hints at unknown forces at work in the comet's frozen heart. The real head-scratcher lies in the comet's outbursts, sudden, violent eruptions that blast gas and dust into space without warning. Traditional models predict these events should occur when sunlight warms the surface, sublimating ices into vapor. But Rosetta witnessed explosions erupting from shadowed regions where temperatures hovered near -200 degrees Celsius. No solar heat could explain them. One radical theory suggests quantum tunneling might be at play, a phenomenon where particles cheat classical physics, slipping through energy barriers that should block certain reactions. In the comet's ultra-cold interior, where molecules move sluggishly, quantum effects could dominate, allowing chemical processes to unfold that would be impossible under normal conditions. Then there's the puzzle of molecular oxygen. When Rosetta detected O2 gushing from 67P, it sent shockwaves through the scientific community. Oxygen is notoriously reactive. It binds eagerly with other elements, vanishing almost instantly in most cosmic environments. Yet here it was, pouring forth as if the comet had secret reservoirs. The leading explanation, ancient ice, preserved so perfectly that trapped oxygen molecules couldn't find partners to react with over billions of years. But even this theory strains credulity, given the comet's turbulent history of collisions and solar heating. Perhaps the most revolutionary idea comes from 67P's dust grains. These microscopic particles, once dismissed as inert debris, are now recognized as nanoscale laboratories. Their porous surfaces create sheltered pockets where molecules cluster, shielded from radiation. In lab experiments mimicking these conditions, scientists have watched simple ices transform into complex organics, no liquid water or earth-like temperatures required. This surface-mediated chemistry could rewrite our understanding of how life's building blocks form, suggesting the universe doesn't need planets to cook up complexity. A frigid, airless comet might be just as effective. Every anomaly on 67P chips away at the foundations of classical physics. Its bizarre chemistry suggests that in the extreme cold and vacuum of space, matter follows rules we've only begun to glimpse. The comet's very existence is a challenge, a reminder that the universe's laboratory operates on a scale and under conditions far stranger than anything we can replicate on Earth. And as we decode its secrets, we're not just learning about a single cosmic oddity, we're glimpsing the hidden laws that might govern chemistry across the galaxy. Long before telescopes or spacecraft, comets blazed across human skies as unpredictable visitors, celestial firebrands that defied the orderly march of stars and planets. Ancient Chinese astronomers etched their appearances on oracle bones, fearing them as broom stars sweeping away dynasties. Babylonians saw divine fingerprints in their tails, while medieval Europe trembled at their glow, interpreting them as God's flaming sword heralding doom. Even Halley's Comet, now a celebrated periodic guest, once sent King Harold of England into battle, convinced its apparition signaled his impending victory, only to perish at Hastings days later. This primal awe wasn't mere superstition. It was humanity's first reckoning with the cosmos's untamed nature. Comet 67P, for all our modern understanding, taps into that same wonder. Its rotten egg stench and duck-like silhouette might lack the drama of a fiery tale lighting up the night sky, but its mysteries are no less profound. Where ancient observers saw omens, we now see quantum tunneling and probiotic chemistry, equally bewildering forces that challenge our grasp of reality. The comet's very existence bridges eras. Its ices formed when woolly mammoths still roamed Earth, yet its chemical quirks speak to phenomena older than the sun itself. In a way, those medieval peasants clutching their rosaries weren't entirely wrong. This cosmic snowball is a messenger, just not of divine wrath. Its payload is knowledge, whispering secrets about how planets form, how molecules assemble, and perhaps even how life began. What makes 67P so captivating isn't just its science, it's the way it mirrors our own evolution as cosmic observers. Centuries ago, Tycho Brahe used a comet's parallax to prove they weren't atmospheric phenomena, but deep space travelers. Now, Rosetta's lander bounced across that same void, turning myth into data. Yet for all our advances, the comet still defies us. Its magnetic murmurs, its explosive outbursts, its molecular surprises, they're reminders that the universe reserves the right to astonish. Every time this icy wanderer spits hydrogen cyanide into the void or cracks open a new pit on its surface, it's not just geology in action. It's the cosmos keeping its oldest magic alive, the magic of showing us how much we have yet to learn. Perhaps that's why comets still quicken our pulse, whether they're streaking past Earth or being prodded by robots. They're celestial wildcards refusing to be catalogued or tamed. 67P's greatest gift isn't the answers it's given, but the questions it forces us to ask. In an age where algorithms predict everything from the weather to stock markets, here's a 4-billion-year-old iceberg that still crackles with surprises. Its story isn't just about physics or chemistry, it's about humility. However far we reach into the cosmos, there will always be another duck-shaped enigma, another whiff of cosmic sulfur, to remind us that wonder isn't just for ancient stargazers. It's written into the fabric of the universe itself. Comet 67P might seem like just another cosmic oddity, an oddly shaped, foul-smelling snowball drifting through the void. But this comet isn't just for scientists in lab coats. Its story is your story. Every element in your body, every breath you take, traces back to the same primordial ingredients that built this comet. When we study 67P's bizarre chemistry, its hydrogen sulfide plumes, its hidden pockets of organic molecules, we're not just decoding a space rock. We're reading the recipe for existence itself. Think of it like finding an ancient cookbook in your grandmother's attic. The pages might be yellowed, the measurements unfamiliar, but the dishes described are the ancestors of every meal you've ever eaten. 67P is that cookbook for the cosmos. Its ices contain the same water that fills our oceans. Its dust carries the same carbon that forms our DNA. Even its stench, those rotten eggs and bitter almonds, hints at processes that might have seasoned Earth's early atmosphere with the raw ingredients for life. This isn't just about curiosity. Understanding comets like 67P could answer one of humanity's oldest questions. Are we alone? If this comet can brew complex molecules in the harshness of space, imagine what's happening on countless others across the galaxy. Every time we discover a new organic compound in its tail, every time we detect another chemical that shouldn't survive, it nudges the odds that life isn't a fluke, but a cosmic inevitability. But there's a deeper reason this matters. 67P challenges our assumptions about how chemistry works. Back on Earth, we've spent centuries studying reactions in labs with controlled temperatures and pressures. This comet laughs at those constraints. It shows us chemistry without beakers, reactions without rules, a universe where quantum tunneling might let atoms cheat, where dust grains act as tiny reactors, and where the coldest corners of space somehow cook up complexity. That's why missions like Rosetta aren't just scientific endeavors, they're journeys of collective discovery. The data streaming back from 67P doesn't belong to any one nation or institution. It's a gift to everyone staring up at the night sky, wondering how we got here. Every outburst, every unexpected molecule, is a clue in the greatest detective story of all. how a cloud of gas and dust became planets, oceans, and eventually, creatures capable of sending probes to chase comets. So the next time you hear about a smelly space rock billions of miles away, remember, you're not just a spectator, you're part of the experiment. Your atoms were forged in the same stellar furnaces that built comets like 67P. Its mysteries are your legacy, and its answers could reshape not just textbooks, but our very place in the cosmos. When bizarre chemistry meets the public imagination, wild theories inevitably sprout, and Comet 67P's foul odors have inspired their fair share. From online forums to late-night conspiracy shows, some have spun tales of alien factories churning out hydrogen sulfide beneath its surface, or hidden dangers lurking in its cyanide-laced plumes. It's easy to see why. That mix of rotten eggs, horse stables, and bitter almonds sounds like something brewed in a sci-fi villain's lair, not a primordial ice ball. But here's the reality: every molecule Rosetta detected has a natural explanation, and none involve little green men or doomsday scenarios. Take hydrogen cyanide, the compound that set alarm bells ringing. Yes, it's lethal in concentrated doses on Earth, but 67P's traces are so diffuse they dissipate harmlessly in space. Far from being a cosmic weapon, this molecule is a cosmic workhorse, a building block for amino acids that's been found in interstellar clouds and even around newborn stars. Similarly, the ammonia and formaldehyde venting from the comet aren't industrial waste. They're relics of chemistry that's been running on autopilot since the solar system's birth. The real magic lies in how ordinary these ingredients are under the hood. Every stinky compound on 67P forms through well-documented processes, just under conditions we rarely encounter on Earth. Hydrogen sulfide, it emerges when sulfur atoms, baked into dust grains during the solar system's formation, finally meet sunlight after billions of years in deep freeze. The bitter almond scent of cyanide, a byproduct of nitrogen and carbon atoms linking up in the vacuum, energized by cosmic rays instead of some extraterrestrial lab. Even the comet's alcohol, like methanol, plumes trace back to simple ices rearranging themselves under ultraviolet light. Dispelling these myths isn't just about fact-checking, it's about refocusing on the genuine marvels. 67P's chemistry is astonishing precisely because it's natural. No aliens needed. The comet's ability to brew complex molecules in deep space without liquid water or balmy temperatures challenges our very definition of where and how chemistry can thrive. Those noxious gases aren't signs of danger, they're clues to a hidden universe of chemical creativity, one that might have seeded planets like ours with life's raw materials. So why do these misconceptions stick? Partly because comets have always been cosmic Rorschach tests, blank slates for our hopes and fears. Centuries ago, their appearances heralded famine or divine wrath. Today, they're canvases for more modern anxieties. But 67P's true story needs no embellishment. Its odors, however pungent, are the scent of discovery, proof that the universe can cook up complexity in the unlikeliest kitchens. And that's a revelation far more thrilling than any sci-fi plotline. Comet 67P's stench isn't just a curiosity, it's a cosmic wake-up call. That mix of rotten eggs, bitter almonds, and horse-stable aromas drifting from its surface isn't merely unpleasant. It's proof that the universe still holds chemistry textbooks can't explain. Every whiff of hydrogen sulfide, every surge of formaldehyde, is a reminder that the rules we've written for how matter behaves might only apply to our tiny corner of existence. Out in the frozen dark, where temperatures plunge near absolute zero and radiation tears at molecular bonds, this duck-shaped comet is playing by a different set of rules, one we're only beginning to decipher. Think of it like stumbling into a hidden laboratory where the laws of physics have been tweaked. On Earth, complex molecules need warmth, liquid solvents, and carefully controlled conditions to form. Yet 67P assembles them effortlessly in the vacuum of space, with nothing but ice, dust, and cosmic rays as its tools. It's as if the universe has been running a parallel chemistry experiment for billions of years, and we've just peeked at the results. The comet's organic, rich ices, its unexplained magnetic whispers, even its violent outbursts in shadowed regions, they're not glitches. They're features of a reality far stranger than we imagined. This isn't just about rewriting textbooks. 67P's mysteries ripple outward, challenging our search for life beyond Earth. If a comet can brew life's building blocks in conditions we once thought sterile, what does that mean for icy moons like Europa or Enceladus? Could the same quantum tunneling that lets hydrogen cyanide form on 67P be at work in the clouds of distant exoplanets? The comet's chemistry suggests we've been too narrow in our thinking, limiting our search for life to environments that mirror Earth's. But the universe, it seems, is far more inventive. Future missions will dig deeper, literally. Probes equipped with drills and subsurface scanners could finally reveal what's happening beneath 67P's cracked surface, where hidden chambers might harbor chemistry even Rosetta couldn't detect. There's talk of sample return missions, of capturing pristine comet ice and bringing it back to Earth, where labs could dissect its secrets molecule by molecule. Every new instrument, every closer look peels back another layer of the comet's enigma. But perhaps 67P's greatest lesson isn't about science, it's about humility. In an age where algorithms predict our preferences and satellites map every inch of the globe, this smelly, misshapen snowball reminds us that wonder still exists. For all our telescopes and supercomputers, we're still cosmic newcomers, piecing together the universe's rules one baffling comet at a time. Every unexplained plume, every anomalous molecule is an invitation, not just to solve a puzzle, but to marvel at how much remains beyond our grasp. So the next time you catch a whiff of something foul, whether it's a forgotten lunchbox or a roadside skunk, remember Comet 67P. Its stench is more than just a chemical quirk. It's the scent of discovery, a signal that the universe still has stories left to tell. And as long as comets like this one drift through the void, trailing their cryptic aromas, we'll have reasons to keep looking up, keep questioning, and keep chasing the next great cosmic mystery.